I5 conservation of momentum and two masses. And the first problem we're going to do is figure skating. Let's look at this problem here. And this problem's inspired by Canadian Figure Skating Championship, that photo here, where we're looking at Piper Gills and Paul Poirier. And the problem is going to be here, inspired from this, is that the one skater is going to run and then jump on the back of the second skater, and then they're going to move together. And since they're on ice, we're going to neglect any friction there and use the conservation of momentum to figure out what the speed would be when they both move together. So we need to have some data here. So let's go ahead and draw a little picture here. So before, we're going to have the situation where we have mass 1, and we'll use U for before and V for after. So this is going to be some speed. We're going to say here 20.0 kilometers per hour. And the mass here will take 50.0 kilograms. That's the mass 1 and mass 2. Now the second person here is at rest, so there's no velocity. And that second person has a mass of 75.0 kilograms. So the question is, what is the speed when they move together after the interaction? And it's a one-dimensional problem. See, in the horizontal direction, there are no external forces. So in that case, we can write down M1 U1 plus M2 U2, that's the momentum before, is equal to the momentum afterwards. So here we have the second mass is at 0 velocity. And what are we trying to solve? Well, they go together at the end. So see, at the end, V1 equals V2 equals some V, because they're connected, moving together. So if that's the case, then this is going to be M1 plus M2. You can factor that out times V, since the V1 and V2 are the same. And what we're interested in solving is that final velocity. So we got a nice equation here that says that this final velocity is M1 U1 over M1 plus M2. Now, it's somewhat subjective preference when you plug in numbers. Sometimes I like to go the distance and have the formula like this. Other folks might say, well, at this stage, I'll just go ahead and plug in numbers here rather than keep it as in symbols. So that would be here 50, and the speed 20.0. And then over here, you have the masses. The first mass is 50, and the second mass is 75, and you have V. So putting the numbers in up at that stage, we have this equation, which gives us 20 times 50 is 1,000. And 50 and 75 is 125. So the velocity is 1,000 over 125. And the answer is 8. That's kind of a neat thing that 125 goes into 1,000 8 times. Of course, you use a calculator here, but like 25 goes into 125 5 times, and 25 goes into 1,000. The 25 goes into 100 4 times, so there's extra zeros. That's 40. So you can kind of see that one without a calculator. And that's kilometers per hour, which is about 5 miles per hour, 2.2 meters per second, 7.3 feet per second. And now we go to problem 2. This is going to be throwing an object on ice. And here we got a nice picture here of a bear throwing something. So in our problem, we're going to give some data and figure out the recoil velocity of the bear. So the bear throws, going to have the bear throw a bowling ball in this particular case. So let's give some data here. So we have the bear is going to have a mass, let's say it's a young bear, 100 kilograms, standing on a sheet of ice. We can neglect friction. And the bear is going to throw a ball, and that's going to be a ball 6 kilograms in the horizontal direction, and that's going to be at, say, 30.0 kilometers per hour. So when they give you that 0.0 like that, that's encouraging you to give a little more significant figures. Here, you'd be, given 2 significant figures, since the most uncertain one has 2 significant figures. So if we do that, the conservation momentum, so the momentum before throwing the ball has to be the momentum after throwing the ball. But before throwing the ball, the momentum is 0. The bear is there at rest, the ball's at rest. So that means afterwards, you're going to have 0. So 0 before has to equal the mass of the ball. So we're going to say the ball has mass m, and the bear's mass, say, is big M. So the ball is little m times the velocity of the ball. We go ahead, and if you want, you can even write down, like I did in the text, I wrote down little subscripts. So if we did this, we then have mass of the bear times the velocity of the bear. So this is my preference at the moment to do this. Then I find that the mass of the bear times the velocity of the bear, that's over here, is minus the mass of the ball and the velocity of the ball. So then the velocity of the bear is equal to minus the mass of the ball times the velocity of the ball over the mass of the bear. And if I want to use that little m and big M, I have a little m over a big M for the bear, the velocity of the ball. So the bear's not going to be moving as fast, because that big M is going to see, when you divide it, it's going to be less, it's going to get you a fraction. So if we do that, we get the velocity of the bear is equal to minus, you plug in for the mass of the ball, 6 kilograms, the mass of the bear, 100 kilograms, and then the velocity of the ball is the 30.0 kilometers per hour. And if you want, you could put the 0.0 there, but you don't even need to put the units in, but you should be careful. I like to put units in so as to remind me I'm doing it right. Kilograms going to cancel and come out kilometers per hour. But if you're careful, you could, leave the units out and put them in at the end. Okay, so this is minus 6 times 30 is 180, and this is over 100, and that's kilometers per hour. That's minus 18 over 10 kilometers per hour, and that's 1.8. So the velocity of the bear is 1.8. Now here, if I leave off the minus sign, I need to indicate the direction. So I might say opposite. For example, you could say opposite the direction of the ball. So the reason why that came out negative is because in our picture, now if we had set this up so that the ball is going, say, in a negative direction, then minus a negative, the bear would be going in a positive direction. So it depends on how you set up the problem, but you can communicate it this way, that the bear is going at this velocity opposite the direction of the ball. So if the ball is going negative in that direction, if you pick your axis, say, to be positive to the right, then you would have a negative 30 there, and then this negative would cancel that. The bear would be going in a positive direction, but by saying opposite direction of the ball, that's pretty clear.